Brave New World, Brave New World. We were able to describe this Brave New World here real quick with our TNB friends. In the last section, we talked about what these things are. We talked about how to find these. We talked about that when we have the unit tangent, the unit normal, and the unit binormal, we are describing this mutually orthogonal frame of reference that's moving with the particle. It's describing where this particle is heading, the instantaneous velocity, if you will, where it's heading with its magnitude. Well, the magnitude's 1, but where it's heading, because we have unit tangent, it's just the direction of that heading. We have unit normal telling us where it's turning. We have unit binormal telling us how it's twisting all through space. That's what these things are, and we talked about how to get them last time. Now, how do we use them? We use them first just to describe the motion of that particle, but we also describe two other things: curvature and torsion. These are two aspects of a space curve, or a vector function, which gives a space curve. Two aspects that describe for us how that curve is changing over time, or over our parameter. We're going to talk about both of them. We're literally just going to talk about torsion. We're not going to do a whole lot of work with it, but we are going to do a lot of work with curvature. So we'll talk about curvature first. Here's how I would like you to just think about curvature. Curvature is a curve's failure to be a line. It's a measure of a curve's failure to be a line. The more it fails to be a line, the more curvature it has. Let's look at this example just real quick. Is this going to have a lot of curvature right here? That looks pretty close. That looks pretty close to a line. Tell me where we're going to get an increase in curvature. So you tell me when. Are you guys ready?
Right there.
Oh, you missed it. I totally thought you would have it that time. I thought you were on the curvature. Yes or no? If there's any, it's slight. How about here? Yeah, we're getting some curvature here. Getting some curvature. It's failing to be a line pretty much. And then we go. Oh wait, how about that? Is that a lot of curvature right there? Remember, curvature. This is going to happen at a point. At every point, there's a measure of curvature. Just like at every point, there's a measure of a heading and turning and twisting. How about here? If this is a measure of a curve's failure to be line, this is an epic fail. Okay, that's really not close to it. That's epic fail. So that's what we mean by this curvature. We're using kind of some not mathy words. We're going to get to mathy stuff in a second. So the more curvy that a curve is, the more curvature that you have. The curvier that we have this vector function, the larger the curvature. That's the more curvy. The more curvy, the function, or piece of the function, the larger the curvature. A lot of curvature? No. Curvature here? Yeah, it's going to have some curvature. Curvature here? Not very much. Curvature? Yes, more and more. Oh my gosh, there's a lot of curvature in the latter part of that function. Head now if you understand the idea of curvature. It's failing to be a line. So the further away from a line that it is, the more curvature that we have. Now, how do we do it? I want you to consider curvature mathematically this way. I want you to think about a certain portion of this curve. It's called arc length, and I want you to think how the tangent is changing. If the tangent is not changing compared to a length of the curve, are we going to get a lot of curvature? If the tangent is changing drastically compared to a length of curve, are we going to get a lot of curvature? Yeah. So what curvature really is mathematically is a comparison between how the tangent vector is changing compared to the arc length. So if the tangent is changing over a period of arc length a lot, you're going to get a lot of curvature there. If it's not changing compared to a period of arc length, it's not going to get a lot of curvature. So it's just this ratio, basically it's a ratio of how the tangent vector is changing with respect to arc length. And that's actually the definition of curvature. So I'll write it in English here real quick, but then we'll start the math over here. So curvature is a relationship between arc length and the tangent vector. Yeah, Brad. Really, arc length compared to tangent vector. More specifically, it's how the tangent is changing with respect to arc length. With respect to. The reason why I write all this out in English, I could easily give you a formula right now, but I want you to understand the formula, how it's related, not just be like, what's all this mean? I want you to get it. Okay, I want you to understand the concept here. Do you understand the concept that if the tangent vector is changing a lot over a certain period of my curve, if the tangent vector is changing, it's going to be curving very rapidly. If it's not changing very much, it's not going to be curving very much. The measure of curvature would be great if the tangent vector is changing a lot over a period of time, or actually arc length, or it would be low if the tangent vector is not changing over a period of arc length. Head nod if you understand what I'm talking about. Now, listen to my verbiage of what I'm talking about here. I said over a period of arc length. This is why we reparameterize by arc length, so that we can compare the tangent vector to the arc length. That's why we did it. Are we going to use it? Yeah, sometimes we're gonna. We have some ways to work around it with the TNB frames. It's nice, but the idea here is that this curvature, lowercase Greek letter kappa, so we say kappa for curvature, is literally just this. It's literally just that. Now, we always consider kappa to be the magnitude of this relationship. This, by the way, if you think about it, this is still vector, okay? So when we take a magnitude, is curvature going to be a vector? If you take a magnitude of a vector, do you get a vector? No, so it's a scalar function. So it can't have t's in it, but that doesn't mean that it's a vector. It's a scalar function. You plug in a number, you get numbers out. But look. How t is changing with respect to arc length. Derivative of t. How t is changing with respect to arc length. That's literally what we're talking about. Show of hands, feel okay with the idea there. That's where it comes from. Now, we're going to make it more notation that you probably are more familiar with. The derivative of t with respect to arc length. The derivative of t with respect to arc length. That's it. That's what curvature is. If you have reparameterized in terms of arc length. Do you guys remember all doing that in that section? We reparameterized, spent a whole lot of time doing it. If you do that, if you take the time to do that, if you take a derivative of your vector function, you get this. Oops. That would be the derivative of the vector function in terms of arc length. But this would equal this, because the derivative of a vector function with a unit length, with reparameterized arc length, let me start over, I completely screwed that one up. The derivative of a vector function that has been parameterized in terms of arc length has a unit magnitude. It's still a tangent, but it's a unit tangent. If I take the derivative of that piece, I automatically get curvature. If I take the magnitude, then I get curvature. this is a big reason why we reparameterize in terms of arc length. Now, here's the problem though. Was it super easy to parameterize in terms of arc length? No, not easy at all. Especially finding the magnitude and doing integrals. That's not fun. It's not so much funsies, okay? And then the piece you get can have a lot of crap in there. So yeah, we can do it. Are there some workarounds? Yes, that's the good news. Okay, so I'm going to give you some workarounds right now, and you are finally going to understand why we're doing all this stuff. Okay, so the big picture. Curvature is an important concept for us. It describes a motion. It describes how our curve is behaving. It's one of these important factors that we have, okay? We can do it if we reparameterize pretty easily. You take the derivative of that reparameterized vector function, you got to give it tangent. Take the derivative of that, fine. And the magnitude, that's automatically curvature. Boom. Is it easy to reparameterize? No. So we start saying, well, maybe there's some other pieces of this. Let's start with this. Let's start with the fact that, so here's a little proof on some other ways to do curvature. You already know one. It's there. It's done. Just some basics. Let's say that we haven't reparameterized in terms of arc length. Still got a little letter T there. Well, what this is the derivative of the unit tangent with respect to t, our original parameter. Pretty basic. With me on this one? However, if we take that and we apply the chain rule to it, so can you apply chain rule? Yes, it's just derivatives. Let's apply the chain rule. If we take this and make this little chain rule substitution, is it possible? Yeah. Yeah, that's that S. That S is just a scalar function. So we can put that in there as just a chain rule. You see that they use your fancy math, your kind of calculus, cross out stuff, and go, oh, I cross it out. It actually does work if you go back to limits. Chain rule works on that. I don't have to prove the chain rule. We're out of that class, so I'm not going to prove it. But this is a true statement. What's also true is that's literally a multiplication. Well, what if I just solve for this piece? You can see why I want to do that. If I solve for this piece, what we get, how would I solve for that piece? Huh? How do you get rid of multiplication in any equation ever?
Division.
Let's divide. There's a couple things you don't really want to do. You really don't want to deal with reciprocals of things that stand for derivatives. So we're going to divide by the whole piece there. It makes things a lot less confusing. You see what we're doing? We're just dividing both sides with this, and I'm flipping them around. So I have this equals this over this. Show of hands feel okay with that one. Now, these are all still vectors. And if I take the magnitude of all of them, that still holds true. But wait a second. But wait. It's awesome. Here's the thing. Do you see this anywhere on the board? Don't lose it. I'm going to bust a kappa. That was funny. The best I got. Don't laugh too much. You're going to hyperventilate. What's this one? That's curvature. This right here is the derivative of the unit tangent with respect to t. This right here that right there, and I'm going to prove this is like a little sub-proof. Sorry, I have to do a sub-proof here. This right here is the derivative of your original vector function with respect to t. This piece, kappa. This piece, derivative of the unit tangent. It's obvious. Derivative unit tangent with respect to t. This is not so obvious. This is the derivative of the original vector function with respect to t. Notice, are any of these in terms of s? No. They're all in terms of t. That means we don't have to reparameterize. This little proof right here, if you want to see it, I'll give it to you. Do you want to see the little proof that says that this is actually, you probably you're up 3 students, so you always want to see this stuff. Here's the little sub-proof. If this is true, which it is, that was the definition of the arc length function by its derivative of the vector function, magnitude, integral, boom. With me? We're kind of doing some sloppy proof here, but check this out. Take a derivative of both sides. What happens when you take a derivative of an integral by the fundamental theorem of calculus when you're going from a to t, and it's really a little u there? What happens when you take a derivative of an integral? What happens? Done. This right here is the definition of ds dt. Derivative of an integral by fundamental theorem of calculus, 0 to a to t, and you'd have little u's there, so sloppy proof. Is that. And that proves that for us. Now, stop for like 10 seconds. Let's absorb this and then go on because there's something pretty neat on the board. Right now, do you know we haven't done any of them, but do you know the process of finding the t, the n, and the b? Whole bunch of derivatives and magnitudes. Put them all together, do a cross product at the end, you're done. Okay, that's t, n, and b. Is it really that easy as I said? Not really. There's a lot of work there. Curvature is a relationship of the curve. It's telling us how we're changing, comparing the tangent to the length of the curve, saying how curvy it is. That's really what's going on. To do it, it's literally comparing tangent to arc length. But this sucks, because you got to reparameterize, so we don't do it. You go, no. Let's prove something here. Boom, 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 boom. This is curvature. Now, and I proved all of it. Go through again if you want to. But check it out. Look over here. Do you see these pieces over here? By finding the TNB frames this way, we automatically get curvature. Automatically. Done. That's pretty cool, right? So if we find T, N, and B, inside of that, we have part of the N. We have part of the T. We have our curvature. Should have answered understand the concept there. That's why we do TNB. Not just because it's awesome, helps us define things, and it's useful, but because we have curvature built into it. Are there any questions on this part of the proof? Because I'm going to erase it. Because I need to talk about one more thing. If you don't need TNB, if you only need curvature, if you don't need the osculating plane, you don't need the osculating circle, you don't need the normal plane, you don't need any of that stuff, there's an alternate formula. I'll make you one suggestion here. If you have polynomials, you guys know what polynomials are, right? No e to the t, no sine, no cosine, none of that stuff. If you have polynomials and you just need curvature, use this formula. If you have polynomials and you just need curvature, use the following formula. the reason why I say polynomials, you probably see it. When I take derivatives of polynomials, they're really nice. Do you see what I'm talking about? Take the first derivative, take the second derivative, cross product. Then magnitude. Take the first derivative, you already found it, take magnitude and cube it. That will give you the curvature way faster than doing this stuff with it, especially with polynomials. TNB frames with polynomials are not fun at all. They are horrifying, okay? Now, if you had to do this with like sines and cosines and e to the t, this is not fun. Because you got to find first derivative, product rules. You got to find second derivative, more product rules. You got to cross product them. Then you got to find a magnitude. That's not fun. So this is used for polynomials when you just have to find curvature. That's pretty much it. Show hands be okay with that. Now, before we get to our example, I'm going to talk. We're not going to do an example of this. We're going to talk about what torsion means. Torsion has a Greek letter tau. It's like this. Kind of draw like a pie, but no two legs, and one of them's going the opposite way, okay? Here's what torsion is. Here's the formula for torsion if you have polynomials. It's nasty. Hey, you can't get that one to go. Okay. That's the formula for torsion. If you've got polynomials, I'm going to give you another formula in just a second, but it's not any better. This is what torsion means, though. I'd like you just to have an understanding of what it means. Curvature is a measure of a curve's failure to be a line, failure to be straight. Torsion is a measure of a curve's failure to be contained in a plane. What's that mean? Write that down. I'll explain in a second. Measure of a curve's failure to be contained in a plane. I want you to think of a roller coaster. So we're starting on a roller coaster, okay? And we're gonna do this. We're gonna go, and we're gonna start doing a loop the loop, but it's loop the loop. Sorry, loop the loop, and we're gonna go a really tight one. So let's go and keep on going. Does that make sense? You're going to feel that, right? You're going to feel just like this. You're going to feel like your airplane is just going like this and going on. Does that make sense? Now I want you to imagine a roller coaster that makes the same size circle, but instead of being really tight, it does this. Is it going to feel different? Well, you better believe it. What's the airplane going to do? Instead of going straight back, what it's going to do is it's going to do this. Do you notice how the wings have to turn? The B is changing this. The B is causing it to twist out of a plane. It's going to feel way different. That B is what describes the torsion for us. Does that make sense to you? It's kind of a cool idea. So that being inside of a plane, yeah, a loop like this, just in a plane, you're going to feel like you're just doing one loop, not twisting. But as soon as you start going like this, you're outside of that plane. Torsion is twisting us out. That's what's going on here. This is what the B helps describe, and I'll give you the definition with the B in it. Torsion can also be described this way. It's a derivative of the binomial vector with respect to, with respect to what? Arc length. For this to work, you have to define its arc length. If not, we have that one, and it's nasty. And then you dot product with n. It is a negative, yeah. So fans feel okay with it, the idea on it. Now, I want to put it all together, okay? We know what T is, heading. We know what N is, turning. We know what B is, twisting. We know that curvature relates how the curve is not aligned. The more it's not aligned, the more curvy it is. We know now what torsion means. If we're not in a plane, we can be curving to the same rate, but also twisting. That's that twist to it. Now we're going to put them together. That's probably the coolest part of this lesson. I love this part. Draw yourself a nice looking curve, okay? I'm going to make a little postulate to you. At any point on a curve, there will be a circle that fits that curve best. There will be a circle that fits that curve best. What do we mean by best? So, circle. Let's imagine that one just for the sake of I can't draw. Good, okay? Here's what we mean by best. Firstly, it's going to just touch the curve. It's not going to go past it. It's not going to miss it. It's going to just touch it. So the properties of this is it barely just touches the curve. Emphasize the just. Just touches the curve. Honestly, you know what we call that? We call it that it kisses the curve. Now we're getting steamy in here, huh? Woo! Told you math was exciting. Just touches the curve, it kisses the curve. We want it to just kiss the curve. In order for that to happen, for it to be the best fit, in order for it to just touch the curve, think about what this would mean. It's got to have, at that point, the circle and the curve have to have the same tangent. They have to have the same curvature. It's got to fit. It's got to have the same tangent. It's got to have the same curvature. And the normal is going to go right through the center of that circle. That's what we mean by the curve of the circle of best fit. So these properties say, okay, we're going to have this at this point. The circle and the curve are going to have the same tangent. The circle and the curve are going to have the same curvature. Listen. If they have the same tangent, is it safe to say they have the same normal? Same unit tangent? I mean, you find a unit normal, it's going to be the same thing, right? So they have a same unit normal. And the unit normal has to go through the center of that circle. You can call it a common normal if you'd like. It will have the same normal. It has to be the same. You get the same tangent, you get the same normal. So same normal, and it's going to go through the center of the circle. or will at least point. It'll point through the center. It's only 1 unit long, so it's going to point through center of circle. Now we have some specific words for this circle. This circle that we're describing here, the one that has, look. Do you notice it's just touching? I'm not a good artist, so it's supposed to just barely touch that. The tangent to this circle and the tangent to the curve at that point, it's the same exact tangent. Do you guys see what I'm talking about? Yes, no? If I find a normal, that normal is going to point through the center of that circle. This is what I just described with all these words. What this circle is called the osculating. Can you say osculating?
Osculating.
Osculating circle. I always misspell this, so I'm going to make sure I got it right. By the way, the Latin word for kiss is osculum. That's where we get this from. It literally just kisses the curve. It just barely touches it. Kisses the curve. It's called an osculum. Osculum in Latin, kiss. So, kiss the curve. That's what it's called, the osculating circle. Now, I want you to think about this. What two vectors right now have to be in the osculating circle, or the plane? The plane's going to contain this osculating circle, right? Even if afterwards I twist a little bit. Right here at this point, this plane is going to contain the osculating circle. We call that the osculating plane. What two vectors have to be in the osculating plane? What two?
Unit tangent vector.
Unit tangent and the? Absolutely. Do you see that if the normal is going through the center of that circle, and we have the same tangent to the circle, the plane that contains the osculating circle is going to contain T and N. Should fans be okay with that one? That's pretty cool. So the plane that contains the circle we call this the osculating plane. Man, it's got to contain the same two vectors that describe the circle, T and N. Now, how about this one? This stuff is so cool. So cool! You just took a test, right? And you did pretty well. What do I need to describe a plane?
Point.
A point, okay.
And a normal.
A point. I have a point. And a what?
Normal.
A normal vector. If this plane contains T and N, what's the normal vector to T and N?
B.
That's not important anymore. I was going to be like, boom, for the B, but rewind the video. It's on there. B. Yeah, hey, if the plane contains a circle, has T and N in it, we describe planes by their normal vectors. If this contains T and N, cross product B is how we describe the osculating plane. And the plane that contains osculating circle, same thing. So, since we need normal for the oscillating plane, B is the normal to the oscillating plane. That's pretty cool. One more worthwhile thing to say about this, then we'll start our example, and then we'll take our break. Because so far, honestly, I've just been crushing you with a lot of theory and proofs and not nonsense, but really cool stuff. But it's probably pretty vague right now. We haven't done a whole lot of work. So I'm going to give you an example here in about maybe 2 minutes after I describe one more piece of information. This circle, every circle has a radius to it, yes?
Yes.
The radius is called, it's horrible notation. The radius is called the radius of curvature. And is the reciprocal of the curvature. Here's why it's horrible notation. The radius of the osculating circle is rho. It's pretty familiar to like spherical coordinates, so it's not very good notation, but that's what we have. We're doing Greek letters, lowercase Greek letters, so we got this rho again. So rho, the radius of the oscillating circle, is equal to the reciprocal of kappa. Now let's think about that for a second. Let's say you got, man, just curvature is huge. This thing is really like a tight spiral. Look at the board. Think curvature is huge, got really tight spiral. Is the radius really big or really small? Teeny circle to fit inside that tight spiral. Let's say that our radius is teeny, like really small. What's our radius? Really big. If you had to make the circle that fit this at a point, that's a pretty enormous circle. Does that make sense? What if you had to make the circle, that's a line. What if you had to make the circle that would fit the line? What's the radius? Do the math. What's the curvature of a line? 0. What's 1 over 0? Infinity. You have an infinite circle. The radius would be infinity. It's so big that it's taking the circle, flattening it out. It's a line. Doesn't that make sense? That's kind of cool, right? That's what's going on here. So, last little piece. There's only one more thing I will ever ask you for. It's called the normal plane. The normal plane is the plane that contains N and B. Notice how B is cutting into the board right now, if this is on the plane. B is cutting into the board. What B is going to give you is this plane that contains every vector that's orthogonal to T. I'll say that again because it's probably not sinking into you. The NB plane, called the normal plane, cuts right into here. It's going to contain for you every vector that is orthogonal to T, every single one of them. Do you guys see it? It's going to cut right in there. So the plane that contains NB. Called the normal plane. And contains all vectors orthogonal to T. How about this? If I wanted to describe, and you guys know this stuff, so I want answers. In order to define a plane, wake up your zone. In order to define a plane, I need a point and good. Do I have a point?
Yes.
If I wanted to define the osculating plane, my normal is B. With me? If I wanted to find the normal plane, the one that has N and B in it, what's the normal to that plane? T. T would be the normal for this plane. We use the word normal way too much. the normal to the normal plane is t. Yeah, it is, but that's weak. That's weak verbiage. We just don't have better ways to say it right now. Okay, that's it. What I'm going to do is I'm going to put an example on the board. We're going to take a break, and we're going to come back and crush the example. So this next example, in my opinion, should be on every single Calculus 3 test ever. Like, it has everything that we will have done in this entire chapter. Everything. So we're going to go through it. It will be on your test. I'm not going to give you a horrifyingly bad one because you're going to see they take a long time, like a real long time. So we're going to do this example, and I'm going to go slow through it because I want to make sure you see every single part. Make sense? Okay. So let's go ahead and I'll write it out, then we'll take our break. Any comments, questions at all before we do that? So find TNB, find the TNB frame, find kappa, that's curvature, find rho, that's a radius of curvature for the circle, the equation of the osculating plane, and the equation of the normal plane at t equals pi over 2. What we are going to do, we're going to find all of these pretending that we don't have this yet, then we're going to go back and fill it out. I'm going to give you at one point in this lecture, tell you where in real life you'd be plugging that value in. I got to go through it at least once so you can find everything as functions, but I'll show you where exactly you would plug the t in to get this problem right as effectively as possible. Does that make sense to you? We're going to stop right now and take a little break. Okay, so we're back to our example. This is the one example that has everything in it. Like I said, a little bit later, we're going to do some harder ones, talking about how to find the t, the n, not so much the b on some of them, and then some equations of other osculating planes and circles. So this little recap says, all right, well, if we have this vector function, this space-through curve, at any point, we should be able to find a few things about it. Number one, last time we talked about movable frames, this idea that as we're moving through space, our frame of reference changes. Where we're headed, the unit tangent. Where we're turning, the unit normal. And where we're twisting, the unit binormal changes at every point. Well, at every point then, we should be able to find the unit tangent, the unit normal, and the unit binormal. That one, in this case, would be going like into the plane. Into the board right there. But it's that mutually orthogonal frame of reference that changes at every single point. Do you guys remember talking about that? The TNB frame, like the IJK, just moving through space. Well, here's the deal. We also talked about this thing called the osculating circle, where at any point on that curve, we should be able to draw a circle that barely touches that curve. Barely touches means it's going to have the same tangent, the same unit tangent, and it's going to have the same unit normal. It has to. If it has the same unit tangent, it has to have the same unit normal. It's going to have the same unit binormal at any point along that curve. Well, that circle, that osculating circle, which means just to kiss the curve, is contained by this thing called the osculating plane. It's a really important plane. We're also going to talk about the normal plane that cuts through at that point of tangency, cuts right through the center of the circle and that point and has the n and b vectors contained in it. That would contain every vector that's orthogonal to t. So we're going to we're going to do this example. We'll find t, we'll find n, we'll find b. That's the unit tangent, unit normal, unit binormal. We'll find the curvature, radius of curvature, and then we'll find the equations for those planes that are really important to describe the motion of a particle at a certain point on a vector function. Do you guys understand the idea behind doing this? I know there's a lot of words in that, but it's kind of a 20-second recap of what we learned basically the whole time last time. Now we get to put it in practice. So, in practice, what would be your first step? Man, do you remember how to even find this stuff? From a vector function, what would you be going towards first? The t, the n, the b, the curvature, or the radius of the curvature?
T.
For sure t. What's the setup? How do you find the unit tangent?
Take the derivative.
Units are always derivatives divided by magnitudes. In this case, it's the derivative of our vector function divided by the magnitude of our vector function. Let's go ahead and do that. I want you guys doing this stuff as I'm doing it. So I want you not just copying, I want you to be trying. So let's go ahead, let's try to find the t together, but I want you to do the derivative right now. So since the unit tangent vector is always defined as the derivative of our vector function divided by its magnitude, this gives us a tangent vector divided by magnitude gives us the unit tangent vector. The direction a particle is heading at a moment in time. That's what we're doing. Hey, right-siders, what's this is probably the easiest part. What's the derivative of the vector function that we're talking about? To get the tangent vector, what's the tangent vector here?
Negative sine.
You said plus?
Yes.
Okay. And then what? Perfect. And now if you're okay with at least the derivative. What is it? Come on, I don't want you losing track of what we're doing here. What is that thing?
Tangent vector.
Is it the unit tangent vector? No, it's just a tangent vector. So it's this thing, but it's not necessarily just the unit. And the unit is what's working for us here. So we want the unit tangent vector. So let's go ahead, let's find our magnitude. So go ahead and do the setup. In your own words, probably in your head, since I've kind of punished you with this, I've tried to brainwash you. The idea for magnitude of any vector, I don't care whether you're talking about vector function or actual vector, when you're finding the magnitude, it's square them, add them, square root them. Also, we mentioned this. When there's a lot of sines and cosines floating around, for goodness sake, look out for the Pythagorean identity because it is going to happen. When you square sine and cosine and add them, you get a lot of ones. So look out for those identities. It happens almost all the time with these sines and cosines. Also, because we're squaring things, anything that's negative or positive, who cares? You're squaring it. It's going to become positive. Don't let that confuse you. And so you get this negative floating around. I honestly don't even write it. I square this and go, well, that's going to be positive sine squared plus positive cosine squared t. Plus, oh wait, how about that one? What's that give us? That 1 is quite important. Don't forget about that 1. So sine squared, cosine squared, 1 squared. We've squared them, we've added them, we've square rooted. Head nod if you got the same thing I got. Super difficult? Not really, as long as you keep track of what it is that we're doing, what we're finding, understand what we're actually trying to accomplish here. Now, can you simplify it? This is great because this is how much? 1 plus 1 gives you square root of 8. So the magnitude of this tangent vector is simply the square root of 2. Do me a favor. I'm going to show you a lot of the reasons why I had you do some of the stuff like unit vectors, how I had you write them. I'm going to show you why that is and exactly how to go about the rest of your problem. But first thing, let's set this up. Since our unit tangent is tangent vector divided by magnitude of said tangent vector, can you guys go ahead and set that up for me, please? What should be on our numerator?
Is it that R prime?
Say that again?
Or parentheses.
Yeah, exactly what you just found.
Negative sign.
Plus cosine.
Plus cosine.
Divided by what, everybody?
Root 2.
There was a certain, there's two things you can do here. The first thing you could do, first thing you can't do, don't leave it like that. That's nasty, all right? You have to write this in at least one of the forms of the tangent vectors that we've talked about. This is a unit tangent vector. You follow what I'm talking about here? So you can do two things. You can choose to distribute this and have negative square root 2 over 2 plus square root 2 over 2 plus square root 2 over 2 with all the stuff in there. Please don't do that for this problem. Unless you absolutely have to, don't distribute that. Do rationalize it, but what do we do with that 2? You see the hopefully square root of 2 over 2 that we're going to be getting here, yeah? What do we do with that thing when we're talking about unit vectors? What do we do with it? Put it out front. I told you to do that, and you're going to understand why after this next step that we do. So instead of having it here, that does not look good. What we do is we pull that rationalized denominator, square root 2 over 2 times this. This is the tangent vector. That's all it is. This is what shortens it or lengthens it to make it the unit tangent vector. In this case, shortens it to make it the unit tangent vector. Should fans feel okay with the unit tangent vector? We've done it a couple times in this class, but I wanted to just make sure we have this from scratch, everything we need to know about it. Head nod if we do, we feel okay.
Is this okay to put it in vector notation?
Absolutely. You can do square root of 2 over 2, the brackets, negative sign, comma, cosine, comma, 1. That's fine too. I don't care. As long as you don't do this, and you're going to find out why really, really quickly. Don't distribute that thing here. It gets really hard to deal with. Think about why. Think about why. We just found t. Right there. Oops, sorry. That shouldn't be there. If you have that in your notes, erase that. That's our next little step. I'm sorry about that one. The unit tangent is this thing. Now, are we done with the problem? Goodness, we're like 1/5 of the, we're 20% done. What's the next thing we would do? That's all I heard. I had a long weekend. I don't want to talk to you, Leonard. Come on, robots. Come on, wake it up here. So I got candy. You get some candy? Not now. You hold on for it, okay? Come on. Don't be gluttonous. You can get it later. Look, the next thing we're going to be doing is trying to find out what would you find? Would you find out the n or the b or the curvature? What would you find? Find the n. Can't find the b without the t and the n. So let's find the n. But wait. How do we go from the t to the n? So the unit normal is the derivative, oh my gosh, it's the derivative of the thing that we just found over the magnitude of the thing that we just found. Now we're going to work on that right now. Listen, you're going to see it as we go through it, but this right here, finding the n, is one of the biggest reasons why we don't distribute this. I'll show you why. Check it out. Check it out. Firstly, when we go about finding the derivative of the unit tangent, this thing doesn't have to be hard. This does not make it harder. Distributing it makes it a little bit harder. Check this out. You know this from derivatives. Do coefficients affect derivatives? You can separate derivatives by those, we call them constants, and they're really coefficients. You can separate that. You can pull that coefficient outside, take the derivative, and put it back. Which means if you've left this out front, here's how you take the derivative. Cover it up, take the derivative, put it back. And that does it for you without having to deal with square root of 2 like 3 times. It's only 1 time. That's 1/3 the work. So this is going to be, okay, I'm going to keep the square root of 2 over 2. That's just the coefficient that's making this unit vector. And then take the derivative of just this piece. Does that make sense to you? That's why we keep that hanging out front. Otherwise it gets crazy. It's even better in the next part. You're going to love the next part. You're going to love the next part. You're going to love like amore. Right? Isn't that? I don't know what that means. I imagine it means something good, though. No? Love? Hopefully it's love, not I hate you, Leonard. But take the derivative of this thing. What are we going to get? Left-siders, you guys get this one. Derivative of this, please.
Negative cosine t I minus sine tj,
Mm-hmm.
0.
0. I like that. Like dealing with polynomials. 0. Nothing. Head nod if you're okay with that one so far. Okay, everyone in class, right now, we have gone ahead, we've taken the, here's the whole recap. To find t, you need derivative over magnitude. We start with vector function. To find n, we need derivative over magnitude. We use the tangent vector. Use a tangent, unit tangent function. So what's our next step here? We've already found the derivative of the tangent vector, unit tangent. What's the next thing?
Magnitude.
This is the second reason why we never watch this. If you want to take the I'm going to get to go up here. If you want to take the magnitude of a vector and it has a scalar multiple, that's what we call that coefficient, the scalar multiple. If we have that, check it out. Because that's being multiplied by your vector, because square roots, you know what magnitudes are, right? Square them, add them, square root them. Because of that, because you have that cool ringtone. I want to hear "In the Club" by 50 Cents. All right. You got that ringtone? No. Whatever. Losers. It's my ringtone. Actually, it's not. Did you believe that for like half a second?
No.
What do you think my ringtone? Don't answer that. I don't want you to judge me. It's probably something dorky, right? Whatever. Frozen. Here I stand, here I stay. Let the storm rage on. It's not hard. You can finish that. I sing the whole. Cold never bothered me anyway. You're gonna leave me hanging the whole time. I hate you guys. Whatever. I don't hate you. I love you. That's why I bring you candy. So listen, if you're gonna find the magnitude, subtract with me here for a second. You have something being multiplied, right? You're going to be squaring, adding, and square rooting. Square roots are separable by multiplication. So if you square this and then square root it, you're gonna get exactly the same thing. Leave it out front. It doesn't affect your magnitude if you don't distribute it. It's just can't forget it, okay? But if you were to do this, so here's the square, just watch, square root of 2, a bunch of crap, square root of 2, a bunch of crap, square root of 2, a bunch of crap, and then you square this, and square this, and square this, it becomes a factor for all of them, because it distributes to all of them. Then you go, oh, let's factor it out. Well, then you're gonna have this big square root, right? But you're going to have the square root of 2 over 2 squared by this other larger big bunch of crap. What is it? This is going to be this piece, this piece, where'd it go? This piece squared. That's what it's going to be. What happens here? Done. Square root of 2 over 2 times the square root of the rest. That's why we don't distribute that. Because when you get to a magnitude, you go, hey, what do I do with it? Well, firstly, don't forget it. It's important. But secondly, all we have to do is write out that scalar multiple, square root of something squared is going to give you back the original piece. And take just the magnitude. Oh, man. Got too excited. I'm rubbing it. Just take the magnitude of the actual piece that gives you your vector. That's all you got to do. So in our case, we go, okay, all this nice little proof, so you don't need it. Love it. Keep your scalar multiple. Take the magnitude. We never ever get negatives when we square things, ever. So this squared, cosine squared. This squared, sine squared, no problem. How much is all that going to give you? 1. Which means that the magnitude of the derivative of our unit tangent is just square root 2 over 2. You guys okay with that one? From here, could you set up the unit normal?
Yeah.
Do that. You're going to see the third reason why we don't distribute that. Now I got frozen in my head. Thanks a lot, guys. Appreciate it. Starting from our vector function, unit tangent takes derivative of vector function over magnitude of vector function. No problem, we rationalize, but we don't distribute. This is unit tangent. From unit tangent, we take derivative of unit tangent. We got it. Don't distribute that. Over magnitude of unit tangent. Magnitude is even nicer. Keep this thing, take the magnitude, square them, add them, square root them. Then the unit normal takes our derivative of unit tangent. Divides by magnitude of the derivative of the unit tangent. Do you see the third reason why we don't distribute that? A lot of times these things simplify, or at least you can put them together easily without having to refactor. Especially if you got some coefficients over here that you've managed to mess up this, oh, not mess it up, but multiply and simplify, you have to redo all that stuff. That sucks. That's not fun. Here we go. This is why I became a math major. I love doing that. It's the best part of math, man, when you do it right. Makes you feel like intrinsically good, right? He's not. No, am I the only super dork people? Yeah, okay, don't answer that. I want to show up hands if you feel okay with what we've done so far. It's not hard to do. You just got to keep track because there's lots to do. This is a problem on a test, man. You got a lot of stuff to do. So the idea is this so far. The idea is if I'm trying to find out where that particle is heading, that's a unit tangent. What we found when we did this is the direction that particle is moving at an instant of time. What time? Any time right now. We have not plugged in a value of t here, so this stands for any time. Later on, we're going to be using that. But this is the heading of any point along that curve. I know that you understand that concept. I'm big on concepts. I don't want you to just be able to do the math. I want you to get what you're doing. This is the heading of any point on that curve at an instant of time. Make sense? From there we go. We also want to figure out the normal to that. So where this is actually turning. Is it turning down, up? Where is it turning? What's the vector of that? We take another derivative, take another magnitude, put them together as a ratio. This is the direction that the particle is turning at any given time. What specific time? Well, we're going to use that in a second. This is at any time it's turning in that particular vector direction. And now if you're okay with that one. Now, we found t, a lot of work, found n, a lot of work. Can you go ahead and find the unit binormal? How do you do that? Do you remember doing that?
Cross product.
Yeah, that's right, because if we have t and n, and we want something that's mutually orthogonal, a cross product gives us that. So when we find our b, this is equal to t cross n. I'm going to write this out specifically, what vectors we're talking about. This is the fourth reason we don't distribute this thing. You're going to like this. Check it out. So our t, can you read the t for me so I don't have to look up here? Read the t. What are we talking about? The unit tangent.
Root 2 over 2 times negative sine t I plus cosine tj plus k.
So we're going to cross t with n. We just figured it out. This cross that. This is n. Still head nod if you're okay with that one. Now, two questions. First question, do you remember how to set up a cross product?
Yes.
Second question, do you remember on some of the properties of cross products we talked about. I don't know if I wrote it down, but one of the properties is if you have a scalar, we got a scalar. That scalar can be separated from the cross product. So when you're doing the cross product, B is going to equal this. Check it out. Check it out. When you set up your cross product, and you have your I, your J, and your K. Hopefully you're watching carefully here. Hopefully you're watching. These pieces are your T. These pieces are your N. This is just a scalar multiple. So where you can put that, stick it right out front. Multiply this times the result. You don't have to deal with that at all. Can you imagine if you were to distribute this all along here, have it right here? It's going to get pretty darn nasty. You guys get what I'm talking about? Don't do that. Just leave it up front. Just don't forget about it, okay? The whole key deal is here, we don't distribute it to make our lives easier, but if you forget it, then your life gets even worse than it was. Make sense? Don't forget it. So let's set this up. I want you right now, I'll give you about 10 seconds, just set this thing up. We'll work on it together. Just set it up. I got negative sine t, cosine t 1. I got negative cosine t, negative sine t. What goes there?
Zero.
Love zeros. Head nod if you're really okay with that. That's the last reason why we don't distribute that root 2 over 2. Does it make sense? We don't do it here because it's nice to deal with. When we take a fraction ratio, we can simplify things. Also with our magnitudes, man, it's super nice. Even with our cross product, don't distribute it. Just leave it hanging out front. You should multiply it later. You're going to be absolutely just fine. Just treat it like the scalar multiple that it is. You're good to go. In fact, the first thing I'm doing right now, before I do anything else, I'm writing root 2 over 2 times a bunch of junk just so that I don't forget about it. That's pretty good advice, right? Because otherwise we're going to get too wrapped up in this. We're going to forget it later on, and then be like, oh man, where'd that root 2 over 2 go? Oh, you forgot it. Let's be real careful also. Do you remember how to do your cross product? Right siders, you get the first one. What's the first two things I'm multiplying here? How much is that going to give you? We're gonna shortcut this. We probably shouldn't because of our sign errors, but we're going to kind of shortcut this a little bit for the sake of time. I got to trust at this point you can do a cross product. This gives you 0 minus negative sine would give you positive sine ti. Head nod if you're okay with that one. Now the next one, before I do anything else, I'm putting a minus sign because the j component gets subtracted. Whatever we get, we're going to be subtracting that. So that's the least I would show you. So let's cover that up. Middle people, you get this one. What's the next two things I'm multiplying, please?
The sine t, negative sine t, and 0.
So that's 0. Then minus,
Plus cosine t.
minus, I'm going to write it. Just so we're absolutely certain. So it's,
Minus negative cosine.
yeah. So, hang on. So 0 minus negative would be cosine t j. So minus, does that make sense to you? Here we had 0, so ignore this. 0 minus a negative, we're subtracting the negative. That's going to be adding, but we have that minus there anyway. So we get that positive cosine t. And now if you're okay with that one. That's typically where the sign errors come from. If you have to write out more steps, man, then don't do it the way I'm doing it. Write out more steps. It's better to get the right answer slowly than the wrong answer quickly. All right, that is nothing for you. So that we did ignore. Lastly, we got this one. Cover up our K. Left siders, you get the last one. What's the next two things I'm multiplying?
Sine.
How much is that going to give you?
Sine squared.
Let me put some print out. You know what? I'm going to drop down a little bit. Probably put some parentheses there to make sure I'm grouping this correctly. So sine squared t. How about the next one? Would I be doing plus or minus cosine squared t?
Plus.
Sine squared, positive, minus negative. So it's going to be plus the cosine squared t. The parentheses hold that together because that is the component of a. Good thing it wasn't a minus. Man, a lot of times, trust me, a lot of times you're going to get some pretty good stuff in here. How much does that give you? So our unit binormal is this square root 2 over 2, and we get sine t I cosine t j plus k. Okay, that was a whole lot of work. It took us a whole lot of time, but I want to make sure it's absolutely clear on how we get those three really important pieces. Show of hands if it is. Absolutely clear. For sure? For sure, for sure? Okay, so let's do the next piece of it. From here, I'm going to have to, man, kind of eliminate this. Shoot, I don't really want to. Can I eliminate this? Is that okay for you? I got to work back over somewhere. So let's get rid of at least this thing. We've got our unit tangent, we've got our unit normal, we've got our unit binormal. Can you find the curvature? Keep in mind, what curvature is, it's just pieces of the stuff that we've just done put together. So let's figure out our curvature. Curvature is this. It's the magnitude of the derivative of the unit tangent divided by the magnitude of the derivative of the tangent vector itself. So if you've done your, now I got to be honest with you, there's other ways to do that. I'm going to show you one at the very end of this section on how to find this without doing TNB, okay? But if you, listen, if you need the osculating plane and the normal plane anyway, you're going to need the T, you're going to need the N, and you're going to need the B. Does that make sense? So if you need those pieces, do it this way. Do it that way, because you got to have the pieces anyway. There are other formulas for curvature. We'll talk about one later. But if you already have this worked out, then curvature is really nice, because it's just a couple pieces put in a ratio. What's that piece? Find it somewhere on the board. Can you find it?
Yeah.
It's done at the very last step of our end. So it's right, let's see, it's this piece, so we're going to follow that down. It's, oh, hey, it's right there. It's that square root of 2 over 2. Over, and the other piece, the denominator is found on the very first thing that we do. So right when we're finding our unit tangent, right here, it's just this denominator. So the curvature is this denominator divided by that denominator. In this case, it's, square root 2. How much is that? 1/2. Now, wait a second. Let's think about what these things mean, because I don't want you to get lost on it. Unit tangent, the way we're headed. Unit normal, the way we're turning. Unit binormal, the way we're twisting. At every single point along this curve, we have a different frame of reference. But wait, curvature is a measure of the curve's failure to be aligned. How can that be constant? Can it be constant? Does it make sense for curvature to be constant? If something's curving at the same rate all the time, then we have a constant curvature. Does that make sense to you? A circle would have a constant curvature. It's at the same rate. What this is, if you want it, man, I'm hoping that you remember this from the intro to vector functions and actually drawing them. This right here gives you a cylinder along the z-axis. Do you guys see it? Cosine squared, sine squared, cylinder, circle, along the z. This is that curve around the cylinder. So basically we're just making this outline of a wire doing circles around the cylinder. That's all that's happening. It's curving at the same rate right around that circular cylinder. Make sense? Now, as soon as we do an ellipse, our curvature is going to change. We don't have that anymore. Now we're curving greater, smaller, all the way around that. But for this circle, we have a constant curvature up the can. That's all that's happening. Show of hands, feel okay with that one. Am I putting it together for you? I understand the concept between that's an actual vector function. It is a curve. It's along the soda can, man, or the paper towel, whatever you want to do, and it's curving at a constant rate. That's all that's happening. Can you find the radius of curvature? This is the easiest part. It's the nicest part. What's the radius of curvature? Remember that the radius of curvature is the reciprocal of curvature. It is 2. Please don't let the radius of the cylinder confuse you with the radius of the osculating circle. They don't have to be the same. Because that thing is not wrapping straight around the cylinder, it's going up. It's going to go up like that. So it does not have to be the same. Perpendicular to that circle wouldn't be in the cylinder. It'd be a little bit off from that. So don't confuse the two. I'd like a show of hands if you feel okay with it, because after this we're going to just talk a little bit more about the oscillating plane and normal plane. Show of hands if you feel okay with this so far. All right, so I'm going to erase this. I'm also going to give you a little piece of advice as you're going through this on your own. If you ever have this type of problem on a test or on your homework or anywhere else, about where you start plugging in values, where's a good place to start plugging in values and where's not a good place to start plugging in values. So let me rewrite this, make it a little bit more concise. So those are the 3 pieces that we have. Could you find the vectors at the value t equals pi over 2? So I want a few things here. What I want to do is I want to figure out the equation of oscillating and normal planes. I want to figure out the point. I want to figure out the unit tangent, the unit normal, the unit binormal, all at that value. So let's start with the... Let's put it down here. Start with the point. How do you figure out the point? What gives you points? Unit tangent, vector function, unit normal, what gives you points on a curve? The actual function itself. So let's find out this point of tangency, point of normalcy. Let's find out the point that I'm actually talking about. So let's take this t, let's plug it into this thing. How much is that? What is that? Come on, guys. I could have more out of you than just nothing. Goodness gracious. Do you understand what we're doing here? Do you understand how to find a point from a vector function? You plug it in, yeah, it's going to give you a vector. But the terminal point is going to give you a point on that space curve. So let's do it together. Left siders, I need more out of you guys. Let's plug in pi over 2. What is cosine of pi over 2, please? 0. Oi. Yeah, that's right. We got oi. Can you write it 0? Sure, I don't care. We're going to get a point here in a minute anyway. Do you have to write it 0? I know. You just leave it blank. That's fine. Middle people, you tell me sine of pi over 2. What is that? 1j. And then, okay, plug in, oh, nasty. Plug in pi over 2. Right siders, what's the last component? That right there gives you a vector whose terminal point is the point we're looking for. The terminal point is 0, 1, pi over 2. Show of hands if you're okay with that one. That is the point. Do you get the point? Like for real? Hello, yes, no?
Yes.
Let's find out the unit tangent at that specific point. So if you put this together, here's what we've done. That gives you the direction of this vector function at any point, forever. This one gives you the unit normal at any point, forever. This one gives you the unit binormal at any point, forever. Now I'm asking you, okay, let's make it more specific. Let's find the actual point. Let's find the tangent vector at that point. Well, that's that time. The unit normal at that point, at that time. The unit binormal at that point, at that time. I'm going to give you about a minute. I want you to find all of them. Let's write the tangent, the unit tangent at pi over 2, the unit normal at pi over 2, the unit binormal at pi over 2, and find all of them for me. Go for it. This is interesting. I like this one. I'll let you finish it. I want to make sure you get the right thing. Go for it. Don't just write down what I'm writing. I want to see you actually do it. Did you try it? Did you do it? Do you know how to do it? Do you know the question? Some of you guys are sitting there not doing much. I want to know if you understand the question. Do you understand that this is not giving you a specific unit tangent? This is giving you a formula to find it. If I want a specific unit tangent, you're going to have to plug in what variable? Well, that's the value for what variable?
Oh, T.
T. Because at a certain time, it's going to give you a certain unit tangent. That's what I'm asking you to do. Plug in the value. You will find, oh look, you will find the unit tangent vector at that time, at that point, because that time gives you that point. So we're finding the unit tangent vector at that point, the unit normal vector at that point, unit binormal at that point. All you do is plug in pi over 2. That's all I'm asking, but I want you to get it. Understand the difference between a formula that gives you a unit tangent at any value and one at a specific value at a specific point. That's the idea here. We are describing the motion of that, whatever this curve is, it's mapping a particle, okay? We're describing the motion of the particle at that exact time, pi over 2, which happens to be at that exact point, where it's headed, where it's turning, how it's twisting. That's what we're doing here. The plane even describes it a little bit better. What plane's it on? What two planes is it on? One's orthogonal to another. What's happening there? We'll do it in a minute. So did you get this root 2 over 2, firstly? Can't forget that one's got to be there. When we plug in that pi over 2, the sine of pi over 2 is 1, so negative I. Cosine of pi over 2 is
0.
How about the k?
Okay.
That's a constant, so it's just don't plug something in for that. There's no t there. There ain't no place to plug in. That's just k. Okay? If you don't have a place to plug something in, don't plug something in. You guys okay with the negative I plus k, for real? The unit normal says, okay, well, here's our formula. I know that pi over 2, cosine pi over 2 is 0, so this is gone. Sine of pi over 2 is 1, so this is negative j. Well, that was pretty easy. I like it when that happens. Head nod if you're right with that one. Let's find the unit binomial. So the unit binormal at that time, still get a root 2 over 2. This gives us 1, so we get I. This gives us 0, no j's. K is a constant there, so constant component, so we have k That's our unit tangent, our unit normal, our unit binormal. It's describing where that particle's headed at that time, at that point, where the particle's turning, what direction it's turning in, at that instant in time, at that point, where it's twisting, how it's twisting, what direction it's twisting in, at that time, at that point. That's the description of this particle in space. It's pretty darn cool. It sure depends if you understand that concept. Now, would our curvature change? We did curvature over there. Is it still the same at any time? If this would have t's in it, then we'd plug in a value of t right now. Make sense? Therefore, the radius is also not going to change because they're based on one another. So I'm not going to rewrite that. The curvature stays the same because it's a constant curvature. We talked about y. Constant radius of curvature. The curvature is constant. It can't change. What we can talk about is this. Please watch carefully. If you were ever doing this on a test or homework or something, and you had to find out the b, I want to show you something right here. Please watch carefully. Please don't ignore this. Check it out. I wanted you to find these 3 things, 4 things, 5 things explicitly, doing all the hard work, okay? So finding the derivative of the tangent vector, finding the derivative of the vector function and magnitude, put them in a ratio. Finding the derivative of the unit tangent and the magnitude, put it in a ratio. And then doing the cross product like from scratch. However, where can you make it nicer? Listen, if you're given a value of t, here's where to plug it in, and here's where not to plug it in. Listen carefully because this will bite you in the foot. Sort of sounds like foot. It'll bite you, all right? It'll get you. Don't plug this in for the unit tangent. Don't plug it in for the unit normal, but plug it in right before you do the unit binormal, and things become a lot easier. You have to have the formulas for the unit tangent and the unit normal. There's no way around getting to this spot right here. There's no getting around that at all. Does that make sense? You have to make it at least this far. Watch. Let's say that we don't do this, because this is pretty nasty, right? You're doing a cross product of some pretty crappy stuff, and it can get way worse. So here's my point. If you're just finding the unit binormal so that you can find these 2 planes, which is what we're going to do, here's what I'd like you to do from here on out. Instead of doing all this other work, find the unit tangent, yeah, we got it. Find the unit normal, yeah, we got it. But if you take these values and plug them in now, watch this. If you use these 2 things, if you use those 2 things, which looks a whole lot easier to me. Look a whole lot easier to you? Write your root 2 over 2 first. 0 minus -1, that's I. 0, 0, oh. No J's, done. 1 minus 0. Same thing, whole lot less work. Does that make sense? Did you follow it? Some of you guys didn't follow it. I can tell you like, You ever whistle? No, never mind. I'm not going to make fun of you by comparing you guys to my dog. Sometimes when I go, and he goes, like that. What is the sound? Look, I want this to be unconfusing. I want you to actually get it, okay? You can spend your time to go through and find all of these explicitly. The only 2, if you have an actual point and you're trying to find the other 2 things, which we're going to in a second, the only 2 you have to actually do are these 2. There's no getting around finding these 2 in terms of t, okay? So you have to find the tangent vector and the magnitude. You have to do that. You got to put it in a ratio. You got to simplify it. You have to take the derivative again and find the magnitude again and get that far. But if you have a value of t, plug it in before you do the b. Plug it in there. Because if you plug it in before you do the b, so basically taking this and this, b is still a cross product. You still have 2 vectors. Plug it in, and you can get the same exact thing. by either doing it this way, which is a lot more work and plugging a t, or doing it this way, find the actual vectors and cross-product them. You can't do it before that, because there's no way to take a derivative if you've plugged in a value here. Does that make sense? So if you plug in t here and then try to find n, you can't do it. You can't do it because there's no t. There's nothing to take a derivative of. Does that make sense to you? You can't do that. So you gotta have the t up to this point, but then plug it in for your b. So fancy you mentioned that concept. If that went completely over your head, well, you got a lot of work in front of you. Do it the way that I showed you the first time, and you'll still get the right answer, but it's gonna be a whole lot more work. So if I were the one taking a test, I said find the equation of the osculating plane and the normal plane. I'm finding t, I'm finding n, I'm plugging in my values, then I'm finding b. Make sense? We'll do one more example at the very end of this, where I'll show you exactly where you would plug that in. Make sense? So you'll get another chance. Now we're back to it. Let's wrap this up. I know it's a long problem, obviously, but it's the only one that you really get before we start kind of crushing some other stuff. Let's find this. Pop Quizno right now. What do you need for the equation of a plane?
Point.
Oh, you need a point. Okay, hey, do we have a point? What else do you need?
Normal vector.
A normal vector, not just a vector, but a normal vector. So let's think about this clearly. If our circle looks like that. The osculating circle is this guy. Listen carefully so you get it. What two vectors does the oscillating circle, and therefore the oscillating plane which contains the circle, what two vectors have to be in that circle or plane? T and n.
Yep.
Got to be there. What's the normal? Because you told me already that a plane needed a point and a normal. So for the osculating plane, this contains t and n. All right, you know it then. What's the normal to that plane then? I know that we use normal way too much. I get it. Please don't always use the normal as the normal. I know it's confusing, but this is just talking about a normal vector at a value. For the osculating plane, hey, osculating plane's right here. You can see it. B is the normal vector. To define a plane, you need a point. You need a normal vector. We've got a point. And we've got a normal vector. Good, now if you're okay with that one so far. Did you guys get the idea that the B is the normal vector in this case to describe the oscillating plane? Oscillating plane's here, B's normal to it, got to use that vector. So point, vector, this way, done. Almost done. Lines and planes get really confused, like with your formulas there. Do you remember how to find the equation of a plane? What's it start with? Do you start with the vector or the point? It's always vector, point, plus vector, point, plus vector, point. We can do components and coordinates. There's also one more thing. Man, I hope I'm not just... I know I've talked at you a lot so far. I get it. But I'm trying to give you every little piece here. Check this out. I said something about vectors. I said, man, you can take out scalar multiples as long as you're not dealing with distance. Are we talking about distance here? Not at all. So if you have b equals root 2 over 2, I plus k, and you're like, hey, root 2 over 2, do you really want to deal with that in a formula? No, not at all. This is the fifth reason why you don't distribute that. Because instead of b, you can take the normal to be any scalar multiple of b, because they'd be parallel, so who cares? Any scalar multiple says, guess what? I'm using that vector because that's a scalar multiple. Get rid of it, and you go, oh, Let's use 1, 0, 1. I know I'm switching function or notation on you. You should be ready for it. I, no J, 1K, done. That's your normal vector. That's the one you should be using because, hey, forget the root 2 over 2. That's crazy, man. This gives you the direction of the B for sure, but all I need for a plane is any normal. Pick the better normal there. Make sense? That's why you don't distribute. Fifth reason. For our plane, we go, okay, how about the equation of plane, specifically the osculating plane? We take component x minus coordinate plus component y minus coordinate plus component z minus coordinate. Don't stop there. That is not an equation. To get the equation, you have it equal to 0. That's the equation of the plane. To keep going, we got x plus z minus pi over 2 equals 0. Typically what we like to do is group our variables. Ten out of 10. 10 out of 10 on a test. At least part of it. But now if you're okay with that one. You know, I want to see if you can try something here real quick. We're going to do the normal plane. I know I've talked over it again, but there's obviously a lot of stuff going on, okay? This is one problem that encompasses like 2 sections. So we're taking some time on it. I get it. Hopefully you're not just going, oh, I'm so bored. If you are, my bad. But I want to make sure y'all understand it, not just getting bored. I don't care about that. I care that you understand it. We talked about the normal plane. The normal plane does this. The normal plane will give you every single vector that is perpendicular to your heading, perpendicular to your T. It's the plane that contains the N and the B. It cuts right through that circle, through the center, along the B. Does that make sense to you? That's what this says. It contains N and B. Hey, if it contains N and B, what 2 things you need to make the equation of a plane? What 2 things do you need? Point and a...
Normal vector.
Don't tell me a vector, because that's a line. You need a point and a normal vector specific. Do you have a point? Heck yeah. Do you have a normal... Do you have a normal vector for the normal plane? Do you have a normal vector to this plane? What is it?
T.
Because this is mutual orthogonal, T is the guy you're looking for. If we contain N and B, then T is the normal. T is the normal for the plane. I want to see if you can do it. Write down the point. Write down the correct vector that's going to give us the normal vector of that plane. Simplify it. Put it in a plane and simplify the equation. Go for it. Give it about a minute. Hey, what's our point?
0.
Perfect. Love it. What's the appropriate vector we should be using? The normal here is what?
T.
Whatever T is. Okay, so I'm going to start that off, root 2 over 2, negative I plus, it's okay? Would you want to use that as your normal vector? Would you guys want to use that as your normal vector?
Yeah.
With equations of planes, you can take any scalar multiple make it nicer, go, hey, that is the equation for a normal. I can take any normal vector, so any scalar multiple says, just take that, let's cover that up. Let's make our actual normal we're going to use, let's make it this one. Let's make it -1, 0, 1. You guys understand how to get from here to here and why we get to. Unless we're talking about distance, you can take any vector, shorten it, lengthen it, take a unit, don't take a unit, it doesn't matter. As long as it's parallel to a normal to that plane, we can define that plane. So this is parallel to this, it's a scalar multiple. That's the appropriate normal, don't even worry about that one. Just take any normal to this plane, it's parallel to t, it's going to work. So we take component minus coordinate. Component y minus coordinate. Component minus coordinate. Did you guys get at least that far? If you simplify this, we're going to get negative x plus z equals pi over 2. Really similar looking planes. The formulas look pretty darn similar. They do describe two different things though. One of them's containing this circle, and one of them's cutting through it. Hopefully, it makes sense on how that looks. That right there is completely switching one of the plane's directions. That's what's going on right there. Interesting. Should fans feel okay with the idea? Any comments, questions, anything about this? We've done a lot. We've learned how to take unit tangents, derivative over magnitude. We've learned how to take unit normals, derivative over magnitude. B, unit binormals, cross product. Where do you plug in the value in that? Do you plug it in after t, after n, or after b? Where do you plug it in? After n, and then your b becomes very easy. Once you have the three vectors here, finding the equation of the planes is quite easy. You're literally just taking vector, even making it nicer, taking vector, making it nicer, using a point and a vector, and you got it. Curvature is just like almost a byproduct of this method. That's what I wanted you to know. So as promised, some more TNB frames minus the B on this particular one. So I want to go through a couple of them. We'll build from difficulty. I want to talk about the T, the N, and the curvature, show you exactly what to do and what exactly not to do depending on what you're asked for. The next example, we'll find the equation of the osculating and the normal planes, and I'll show you where to plug in values. So here we go. When we're trying to find the T, N, and curvature, where do we start? We're going to move fast, okay, very, very fast. Where do we start with this stuff? How do we start? T, N, or curvature? T. And so our T says that we take the first derivative divided by the magnitude of the first derivative. When we find the first derivative, if you want to check back in your notes, we've actually done this problem before. We found the magnitude. So we're going to go really fast through finding this, but here's how we do it. You got product rule. We'd probably simplify this a little bit. That right there is the first derivative. Next question. What do you do next? Provided you can, and if you don't want to write down all the work, just write down the derivatives, that's fine, okay? I don't want to just crush derivatives right now. We've done the problem before. That's why I told you don't need to write down everything. I just want to go through the process a few times to get the habit down in your head, to get the ideas down. Once we find the first derivative of the vector function, what should you be looking at doing next?
Number 2.
magnitude says square the components, add the components, square root the components. So this stuff squared. This stuff squared, this stuff squared. Now, I'm going to cheat a lot. We've already done this. There was a whole lot, and you can see it. You'll see it right here. Watch. First, did you see where it comes from? You see the e to the t. We have 3 of them. E to the t squared. You factor it. You take the square root. You're going to have e to the t. What you're left with is a whole bunch of cosines and sines. It all simplifies down to 1, 2, 3. You're going to have root 3 e to the t. It's going to look familiar because we've done it. This is root 3 e to the t. Head nod if you're okay with that. We've done it before. I want to skip some steps if we can. Now that we've found the first derivative and the magnitude of the first derivative, what one of these pieces can we find right now? The t, the n, or the curvature? The t and part of the curvature. So for our t, we have nastiness. Divided by this magnitude. I need to make sure that you guys are okay right here before we go any further. Head nod if you are. So, unit tangent is derivative over magnitude. Got it. That's exactly what we've done. Now, there's some pieces that you can deal with here. Check this out. You know that you can factor out scalars, right? From vector. Well, that also means you can factor out scalar functions, things that just give you numbers. If you plug in a number, that's like 0 or 1 or whatever, you're going to get a number here, the same number here, the same number here, and the same number there. Does that make sense? Hello, are you guys with me?
Yes.
That means you can factor that and simplify it. If you want to do the cheating way, okay. If you have e to the t in all 3 components, these are all gone. Now, tell me right now with what we've learned in the very last example that we did, what are you going to do with that root 3? Are you going to distribute, or are you going to move it out front? You can't leave it here. And you're going to change it to... What's the last component that I'm going to have, please? Yeah, don't forget about that. Even though we simplified it, we still do get the 1. Show of hands if you're okay with that one. We're about a third of the way done. Well, probably halfway done. Because once we find the next one, curvature is easy. What's the next thing that we do? Provided we have now the unit tangent, what would you do here? Let's find the unit normal. Keep in mind that the unit normal is the derivative of the thing that we just found divided by its magnitude. Let's work on that derivative. True or false? To find the derivative, you have to distribute the root 3 over 3. True or false? To do the derivative, you have to at least keep the root 3 over 3.
True.
Okay. So next derivative tells us, actually, it's nicer. There's no product rule. There's nothing fancy. We do first component. Second component. Derivative of 1 is 0. Third component. still with me? Yes, yes, no. Okay, so we found derivative, found magnitude, made unit tangent. Found derivative again, found, ooh, what's the next thing we're going to do? Let's do magnitude. When you're finding the magnitude of something that's written in this format with my scalar multiple out front, what do you do with that scalar multiple? Do you put it in the square root or not?
No.
If you did, it would be a factor. You would square it, but then square root it. You get the same thing back again. Just make sure it hangs out. It is important. You don't lose it. But the things that we do in here are just square that's the vector, the magnitude of the vector. Square them, add them, square root them. So here we're squaring this entire component, not the pieces. Please, not the pieces. Square the entire component. Square them, that's 0. Add them, square root them. Here's what this works down to. You probably can see it right now. If you factor out that negative and square, it's going to become positive, or you just multiply everything out. It's going to be the same thing. You're going to get a whole bunch of sine squared plus cosine squared. In fact, you're going to get 2 of them. This is 1, 2. Now, it's not 1, 2. This is 1, this is 1. It's not that. But put them together, and you're going to get 1 plus 1. You're going to get 2. So this whole thing is 2. Which means that under the square root, we have... Go ahead and work it out if you want to, but this will be the square root of 3 over 3 times the square root of 2. Or you're going to get square root of 6 over 3. Should I feel okay with that one? Do we have enough to make up the unit normal?
Yes.
Let's do it. The unit normal takes the derivative, the nasty part. And divides by the magnitude of that. A square root of 6 over 3. That's kind of up to you to be able to simplify this thing appropriately, but it's not that bad. What are you going to do with that square root of 6 over 3?
Cancel out square root of 3 over 3 and just get square root of 2.
Close. It's going to be 1 over square root of 2. So when you do this, you have this divided by this. You would multiply by the reciprocal. Looks like this. Like that. Looks like that. This would be 1 over square root of 2. That's what that would be. And that's going to be square root of 2 over 2. Now we have the unit tangent, and now we have the unit normal in about the most simple forms that we can work with. The last question, this is probably the easiest one. Love finding this. Can you find the curvature given that we've already done all this stuff? Yep.
I had a question. Right there where we cancel out we'll factor out the d to the t, shouldn't it be 1 at the end?
It is.
Then down right below that.
When you take a derivative
Oh,
of
okay.
it, derivative of 1 is 0. Hey, do you all remember the formula for curvature? Honestly, do you remember the formula for curvature? I rarely do. I honestly rarely do. That's why I have a note card. That's why you write it down. That way you go, oh, what is, looks like it's the magnitude of the derivative of the unit tangent divided by the magnitude of the derivative of the vector function. So, I'm going to double check. It's this. over that. If you're not familiar with it, that's fine. If you memorized it, perfect. But if not, don't guess at it. All right? Just reference it. Make sure that we're dealing with the right pieces. It's typically not that bad. You just got to remember where they go. The magnitude of the derivative of the vector function, this is always your denominator. And what you find over here, the next magnitude that you find is always your numerator. So here we go. Curvature is that guy divided by this guy. And if we simplify, we get the square root of 2 over 3 e to the t. What we just did, find the curvature, or that curvature has a t in it, which means at every single point our curvature's changing a little bit. We expect that with vector functions. That we're moving through space, they're curving at different rates, they're curving in different directions. Your curvature should also be changing, but that's how we go through it. We found the t, the n, and the curvature. For real, show of hands, feel okay with that one. Okay, tell you what, we're going to start one more. We're going to go ahead and find you know what, let's stop right there. We'll stop there. Next time we're going to go through and I'll do one more example of osculating plane and curvature and show you where to plug values in. All right, so as promised, one last example. There is definitely a method on how you find equations of oscillating planes and curvature if you're given a value. There's some things you do, I know, whatever, and some things you don't do. So as I just mentioned, it's going to suck for about 10 minutes, and then it's going to get a lot nicer. So let's go through this. Do you remember how to find the equation of the osculating plane and the curvature? It was a while back for us.
Yeah.
A couple days. Goodness. What do you do? What do you start with? We need a few things. We need T, we need N. Do we need B for the osculating plane? No. Keep in mind that osculating plane contains T and N. Do we need B?
Yes.
What do you? Okay.
Yeah.
What do you need to define a plane? A point and a normal. If this plane contains T and N, do we need B?
Yes.
That would be the normal vector.
Yes.
So we need T and a B. That's what we need. Now, how you find them. Don't go crazy and find all of it formulaically. I think I made that up. Like the algebraic formulas, all that. Don't do that if you have a value. So I'm going to show you exactly when and when you cannot plug that value in. Please mind this when you're doing your own examples. I will save you a tremendous amount of work. So here we go. Number one thing we're going to do, we're going to go through pretty quickly since we've already had a hack at this a few times. Number one thing we want to do is derivatives because we're trying to find the T, the N, and the B. So how we do it, like I said, first 10 minutes, going to suck. Here we got I, derivative of that is 0, derivative of this is plus 2tk. So far so good? Now, in order to find the T, I also need magnitude. Magnitude, in your own words, should be the idea square them, add them, square root them. So we get 1 squared plus 2t squared gives us 4t squared. Square them, add them, square root them. You guys okay with the derivative of the magnitude? Hello, yes, no?
Yes.
So far, not too bad. So, what have we found when we put these things together? T. So the unit tangent, which is what we found, takes the derivative of the vector function divides by the magnitude of the derivative of the vector function. And now if you're okay with that one. Now here's the issues we begin having. This is not a vector. This is a vector divided by a function. You need to make it a vector. And what we don't do, I know I told you to pull out scalars and leave them. That's true. But don't pull out scalar functions and leave them. Things with t's in them, do not do that to your vectors. Okay, don't do that to your, that felt really weird. Don't do that to your, okay, don't do that to your vectors, because when you do, you'll have product rule all day long. That sucks, don't do that. So what I expect from your t is to, there's no way to do it well without having your fractions on each component. Okay, that wasn't too bad, but do you see what we're talking about? What I don't want you pulling this thing out, rationalizing 1 plus 4t squared over 1 plus 4t squared times a vector I and 2tk. Do not do this. Do not do it. And the reason why you don't do it, because if I tell you take a derivative, this is a product rule, scalar function times vector function. You'd have to have a product rule that has a quotient rule. That's nasty. Don't do that. That's freaking crazy, okay? Seriously? No, don't. It's easier, not fun, but easier to take it component by component. Head nod that you're with me so far. So we just found derivative, magnitude, put them together. We got unit tangent. This is the heading of any particle along that curve. That's what we got. We got the, yes, go ahead.
It's supposed to be a K?
Yeah. Oh, sweet. Mess up one little thing, huh? You guys got to catch me on that one, okay? Okay. I was getting so excited about this stuff. I was just rolling with it. Probably everyone's going, "That's supposed to be a K." I'm not even listening to you because it's supposed to be a K. I can't even hear you right now. Do I need to repeat the whole thing? I hope that I don't. Yeah, yes, I do. Derivative, magnitude, put them together. Unit tangent. This is the heading, just the direction of the heading of a particle moving along that curve at any point in time, in space. That's what we're doing right there. So unit tangent, done. Now, we just talked about, to figure this out, we got to have t and n, because we got to cross them to get b, so we can define that plane. If the Australian plane contains t and n, the normal would be the b. We've got to have t and n to find the b. There's no way around that for us right now. Okie dokie? So, your next step, what would you do? Yeah, the normal, the unit normal is the derivative of this over the magnitude of the derivative of this. So now we start working with this is where it gets not fun. Not fun. Because in order to take the derivative of this and this, you need at least a product rule here. You need at least a chain rule here. Do not use the quotient rule when you have constants. I'm not even going to use the quotient rule here. I'm going to use the product rule. So I'm going to bring that up. I'm going to think about it as negative 1/2. So the derivative here is our, let's see. I can't, guys, I don't want to be on my head. So negative 1/2. That. So we got negative 1/2, inside stuff is negative 3/2, derivative inside stuff is 8t. And then I plus. You guys okay with that one? If you think about this as 2t times 1 plus 4t squared to the negative 1/2, we'll have a product rule. Derivative of the first times the second plus the first times the derivative of the second. J. That's why it sucks. Dang it. At least you got me this time. Just like J's. What's the problem? Just J. My bad. It's been a long day. Long day. Thanks for catching that. So this is nasty. And what do you do next? What do you do next? Magnitude. Do you want to do it now? No. So simplify this stuff. So when we simplify this, You guys, can you check my work too? Obviously, I'm making some mistakes with J's and K's. Thanks for catching me, but catch some of this other stuff too. What do we got? 8? I think so. We can have it down too. Yeah, 8. This whole thing is the K component. It's the K component. Can you make it better? The answer is yes. How do you make it better? You all right with this? Hmm? How do you make it better?
Factor.
Can you check the train one on the top? Is it supposed to be plus 15?
Here?
Yeah.
Oh, you know what? I outsmarted myself. I did the -1/2 and then put -1/2. So, yeah, thank you. I know calculus good. Awesome. Trying to go too fast for my own good. Sorry about that. Let that be a lesson to all of you. Try to go so fast, make mistakes. Do it all the time. Does that look good to everyone else? Anything else? How you make it better? Get yourself a common denominator. If you do that, I would multiply this by 1 plus 4t squared over 1 plus 4t squared. What that does, that creates this 3/2 with a 3/2, and we distribute that. If you just, man, I shouldn't be doing it, but I have to move fast on this, I'm sorry. If you do distribute this, you get 2 plus 8t squared minus 8t squared all over a common denominator of 1 plus 4t squared to the 3/2 power. So this whole thing becomes 2 over this. I'm not going to particularly ask you if you're okay with algebra right now. What am I? Because I obviously am not. Just kidding. What I'm going to ask you about is, do you understand how to go from here to the t, and how to at least set up the derivative of your unit tangent? Show of hands if you do. You feel okay with that one. Now, stop right here. Ready? Stop. Stop. If you have a value of t, plug it in right now. This is as far as you need to go. Do not find the magnitude through algebra, because finding the magnitude by algebra, or not algebra, but algebra, find the magnitude by vector algebra, or plugging in the number and find the magnitude is going to give you the same thing. Do not go any further if you have a value of t. Are you clear on that? For sure, don't go and find b. That's insane. This thing's getting nasty very, very quickly. Do you guys see what I'm talking about? You got to square this atom. That's not even the bad part. You could actually do it. It's not that bad. But then when you do cross product of that thing and you start working with the t and the n, that sucks. So right now, as soon as you find derivative, and you have to do it up to here. You got to do derivative and magnitude, put them together, and at least find the derivative. Even right here, yeah, I know I made you do the algebra, but even right here, could you plug in a value for t?
Yes.
Yeah, you could. It's going to be ugly. It's probably easier to do it right here, but you could do it. So right now, stop and plug in the t. Don't go any further. If you are given t equals a, plug it in now. I hope that you recognize what I'm telling you. It's pretty good advice. If you go ahead and try to find n, finding magnitude and putting this together, it gets pretty nasty. If you go ahead and find b, that's really, really nasty. That's not fun at all. And then using that for curvature, still not that great. You with me? If we plug in t, things become a lot easier. So let's do that. Let's figure out what's happening. What's happening t equals 0? I want to do a little bit of a recap because it's going to lead you onto why I'm doing what I'm doing right here. So check it out. If I want to find the oscillating plane, here's what I need. You should know. What do you need for the equation of a plane?
Point.
A point. Do I have a point? Really?
No.
Do I have a point right now?
No.
So I'm going to have to find me a point. Right? What else do you need?
A normal vector.
A normal. The normal vector in this case is b. So I need t and n so that I can find b. It's the only reason why we're doing it. If I can find the t vector and the n vector, the actual vectors at that point, then I can find the b at that point. That's fine. But we needed to go this far to be able to do it. We can't stop here. You can't just find me the t, because if you plug in a number here and try to take a derivative of a constant vector is 0. You have to at least get that far. Make sense? From here, everything's fine. So what we're going to try to do is we're going to try to figure out the point. So the point. Can you tell me what the point would be? How would you find the point? Would you use t, n, vector function, q, r, z? I don't know. What would you do to find points? What gives it to you?
T.
What? This give you points? No. What gives you points? This gives you points. Can you plug in 0?
Yes.
What are we going to get? 0, 1, 0. That's what we're going to get. 0, 1. We get the vector 0, 1, 0, but its terminal point is 0, 1, 0. This is given by r of 0. R of 0 gives you 0, 1, 0. You sure you're okay with that? Yeah or no? I gotta know.
Yeah.
In order to find the oscillating plane, we also need to know what the unit tangent is at 0. We need to know what the magnitude of the unit tangent is at 0. Oh, sorry. T prime. Yeah, we're gonna do that. Let's start here. So can you tell me what the unit tangent is at 0? Where would you go for that one? So we did point, we plugged into the vector function. I need to know the unit tangent. I need to know the unit normal. I need to know all that stuff so I can find b. So what's the unit tangent at 0? How much are we going to get? Plug in 0 here, 4 times 0 is 0, 1 plus 0 is 1, square root of 1 is 1, 1 over 1 is I. This one's pretty easy, because there's no j, and this is 0, so we're done. The unit tangent at 0 is simply I. So far, so good? Okay. Now, I also want to find the derivative of the unit tangent 0. Notice something. I do need to find n. I do need to find that, but I don't have it. I don't have it right now. All I've got is the derivative. I made it like halfway. But it's okay. If we can find the unit tangent, the derivative of that unit tangent at 0, then I can use that to figure out what n is. So bear with me here. Just plug it in. Basically, plug in 0 everywhere you've got places to plug it in. You plug it in at the vector function. We plug it in for t. Plug it in here. What's the derivative of the unit tangent at 0? What is that?
2k.
So this would be 0, 2k. Okay. Notice something. This is why you have to go at least this far. If you try to take the derivative of this, how much is it? It ain't this. That's why you got to go at least this far. Now let's wrap this up with something else. Can you find the magnitude of that function? How much is it? Should be kind of obvious. It's only got one component. The length has to be 2. It says, wait a minute. Square them, add them, square root them. Okay, fine. You want to be pedantic about it? All right, cool. But it's got a length of 2. Hey, what can you tell me now if you have the derivative of the unit tangent and the magnitude of the derivative of the unit tangent? What can you tell me? Come on, put it together. What can you tell me?
No.
Yes. So with these two things, I can find the unit normal. But I can only find it at 0. That's the drawback. So if you have a point, yeah, you can find it, but it only works for that point. You got any other number, you got to redo it. You got to at least plug in a different number. So this would be this over this. Looks like K. Should fans feel okay with that one? True or false? I have enough right now to find B.
True.
Do I have T?
Yes.
Do I have N?
Yes.
I can find B. In fact, if you man, you guys should know it. If you have I and K, what's B? It's got to be J. It's got to be J. It's got to be the mutual orthogonal. It's going to be J. We're going to do the cross product. You'll see it, but it's going to be J. Make sense? Now, true or false? I have enough for curvature. Do you remember what curvature is? Curvature is the magnitude of the derivative of your unit tangent. Do I have that? How much is that?
2.
Perfect. Divided by the magnitude of the derivative of your vector function. I also have that, but I haven't evaluated it. So let's go ahead and do that. So take that. Oh, we got it right here. Let's plug in 0. How much? Oh, sorry, this one. Plug in 0. How much are you gonna get? Did you lose it? Okay. Sorry. I know there's a lot going on. The idea behind it: derivative, magnitude, unit tangent. Derivative again. We should be taking another magnitude again. That would be unit normal. But don't do it. Plug in numbers first. Right here. So we got, okay, unit tangent, plug in a number. You got I. Derivative, plug in a number. You got 2K. Find the magnitude just of this guy. You got 2. Divide these like the unit normal says to do. We have our unit normal. Curvature says, okay, you already have this piece somewhere up there. You're going to have this. If you've been, even if plugging in points, whatever, you're going to have this. It's right there. It's 2. This piece, you will have already had some expression, some equation over here somewhere. Plug it into that. So if I plug in 0 here, how much do I get?
1.
Then our curvature is 2. You shouldn't get anything with t's for your curvature if you've plugged in points. All right, so there's no t's involved. It's not constant curvature, but there's no t's involved because at this particular point, at that particular time, I've got a unit tangent of I. Its heading is I. The way that it's turning is K. That's the direction it's turning. The way it's twisting, I don't know, we haven't figured it out yet. Its curvature at that point is 2. The radius of the osculating circle would be what? Perfect, the reciprocal would be 1/2. You could draw a circle that's a radius 1/2 units, whatever this is. Now we're almost done. You told me that we need a point. So we found curvature, so that's check. Got it. We found curvature. Done. We need a point and a normal vector to find the equation of a plane. Do I have a point? That's what this whole thing's based on. Do I have a normal vector? Kind of confusing. We use normal way too much. If I'm looking for, I think it's the 3rd time I've drawn this circle. If I'm looking for the plane that holds this circle, I want that vector. That's the normal vector. I know it's the B, but it's the normal vector for that particular plane. So even though I know that's the normal, we use normal way too much, I'm looking for the B here. So the point is here, the normal vector has to be B. Now, everyone in class, right now, how do you go from T and N to B? What do you do?
Cross
Okay, we can set that up. If you're smart about it, though, you go I, K, cross I and K, you are going to get J. For sure. Mutual orthogonal has to be that. If you really want to show it, you go, okay, well, B equals IJK. And you go, well, T is 1, 0, 0. N is 0, 0, 1. 0. Oh, here's J. 1 minus 0. So, isn't that right? 0 minus 0, that's I. Minus 1 minus 0. 0. Question to you, does it matter? Does it matter if you have negative J or positive J? It doesn't matter. It depends on the order in which you do the cross product. So positive, negative, it doesn't matter. Honestly, I would probably do it this way. So, well, hey, B equals I cross K. We have to get J. We have to get that. So your point is 0, 1, 0. Your normal is J. Can you go ahead and spend a couple seconds? Can you please write down the formula for the osculating plane right now? Could you do that, please? I don't want line. I want osculating plane. So your normal 0, 1, 0, your point 0, 1, 0, you really can't screw this one up. No matter, even if you get your points mixed up with your vector, I mean, you literally can't. You can have 0, x minus 0, plus 1, y minus 1, plus 0, z minus 0 equals 0. You're going to get y equals 1. True or false? That's a plane. Yep, that's a plane. So what's going on right here? What we've done, for that curve at that time, we've found a lot of stuff. We found the heading of a particle, the turning of the particle, the twisting of the particle, direction is twisting. We found the plane that holds the osculating circle, which would be the circle of best fit, that kisses the curve, that has the same curvature as that curve at that exact point. That's everything we've done. We found the curvature of the curve at that point. Does this make sense to you? Could you do it? Next time you do one of these problems, do you know where to plug in the value? Derivative, magnitude, another derivative, plug it in. Then you can find the magnitude separately. You can do a cross product separately. It'll just give you all the stuff at that exact value, at that exact point. Plug in the vector function for point, unit tangent, derivative, magnitude, unit normal, cross product, unit binormal, then we get the plane. That's the idea. Now, you're going to want to see this. Did you get this?
Yeah.
This is the way to go. But, and that's a big but. Cannot lie. Anyway, seems too much. I like it. Cannot lie. You're the brother, whatever. Listen, if you only need curvature, so if you take, please listen, if you only need curvature and you have a polynomial, there's a better way to do it. that begs the question, should I use this if I don't have a polynomial? No. Do TNB, easier. Should I use this if I need anything besides curvature? No, because it won't give you the T and the N. It won't give you the B. It just gives you curvature. So if you have need to find an oscillating plane, don't do this. If you just want curvature and both together, and you have a polynomial, this is easier. It doesn't look easier, but it is easier. I'll show you. We'll go fast. Here's the first derivative. It is that. With me? The magnitude of this is that. The second derivative is 2. If I cross product these two things, we get negative 2j. If I want to find the magnitude of that, well, square them, add them, square root them, or you just go like the 2. Done. So curvature equals this piece over that piece to the third power. 1 plus 4t squared to the 3 halves. You see where the 3 halves coming from? I got a square root to the third power, that's 3 halves power. That's how quick you can find curvature if you have a polynomial. Without polynomials, it gets pretty nasty because these derivatives don't reduce for non-polynomials. With polynomials, it's nicer. So you win some, you lose some. If you have to find oscillating plane, this does not do it. It doesn't do it at all. Now, question, does it work? At t equals 0, can you plug in 0? Let's do it. At 0, you get 2. 2. Same stuff. So if you're given a problem, just curvature, do it this way. Did you follow that, by the way?
Yeah.
First derivative, second derivative, magnitude, put them together. After cross product, you're basically done. Last one. This is pretty cool. No one covers this stuff, but you're gonna get it. You're gonna get it. I've only seen it one time in my life, someone actually showing this, but sometimes you get some weird stuff, some real weird stuff. Find curvature of y equals x cubed plus 1. Ladies and gentlemen, is that a vector function? No, that's just a cubic that's been shifted up 1. How can you find curvature of that? Well, there's a formula. In fact, there's a formula for every single one of these. And they're all different. And you're not going to learn a single one of them. Because that's a stupid way to do it. Well, not stupid. There's just an easier way, in my opinion. If you have y equals a function x, or g equals a function of y, or parametric, oh my gosh, do you like a regular old vector function? Or r equals a function of theta, that's polar. If you have any of those, what we're going to learn right now is there's a way to do it without having a formula. It's called vector encapsulation. Here's the main idea. You guys know about dependent and independent variables, yes? What's the independent variable? X is. What's the independent variable?
One.
What's the independent variable?
T.
What's the independent variable? Perfect. Call the independent variable t, and then the function becomes a function of t, and you can encapsulate it in a vector. For instance, if we had a function y equals a function of x, what's the independent variable? There is no z. There is no z. There's no spoon. This would work. That's the same thing. It's the exact same thing. X becomes t, then y is a function of t. Just call the independent variable t. For here, what's your independent variable? Then this would be a function, x would now be a function of that independent variable. This one's my favorite one ever because you're literally not doing anything. Hey, if x is a function of t and y is a function of t, you get, oh my gosh, a vector function. That's a vector function, that's a vector function, that's a vector function. This stuff works now. This one's a little bit weird until you remember what x and y can be defined as. So with any polar stuff, you know that x is r cosine. And I know I'm forgetting the theta, but I'm using t. And y is r sine. If r is the function, then we have f of t cosine t, f of t sine t, 0. Let me show you how it works with this stuff, and then we're good, okay? So here you go. So let's take this problem and let's force it to be a vector function. Force it to be encapsulated by a vector. If we do that, what's my independent variable? Everyone really quick. Oh, that was really slow. What's my independent variable? Everyone really quick. So this vector function would be, instead of x, I want t. What do I want for my y? Do you see that if I let this work for me, if x is t and y is t cubed plus 1, that's still x cubed plus 1. It's just in a vector form. You with me? If you don't like this, you can make it ti plus t cubed plus 1j. You can do that too. It doesn't matter. Now, question. If I'm just asking for curvature, which I am using curvature, would you do TNB or would you do this stuff right there? Let's do that stuff right there. I got that. The magnitude of this, square them, add them, square root them, is that. Is that. I know second derivative is that. If you do the cross product, I'm just going to have to give it to you, but if you do the cross product, I know you can follow this. Can you follow the magnitude? Can you follow the second derivative? If I cross product this and this, which you know how to do, you got 1, 3t squared, 0. You got 0, 6t, 0. If you cross product that, what we end up getting is simply 6t. J. Oh, sorry, K. Therefore, the magnitude you tell me, what's the magnitude of a vector that has a single component? Square it, add it, square root it. You're just going to get 36t squared under square root. Head nod if you're okay with that one. So our curvature looks like this now. Take that 6t, divide by the magnitude cubed, magnitude of the first derivative of the vector function cubed. And that's it. Now, could you find the curvature at any point along that curve? A lot crazier than it looks like it's going to be, right? It's just a cubic, but that will give you curvature at any point along that cubic. Are you with me on this one? Last statement, then we're done. Last statement. How would you find maximum curvature? How do you find maximum anything? Derivative set equal to?
Zero.
Critical points. So if you want to find the derivative of this thing, what we end up getting your denominator cannot be 0. It's all positive. Set your numerator equal to 0. You'll find out the time or times when our curvature is maximized, when we're curving the most on whatever this curve looks like. That's the idea. Are there any comments, questions at all? So if you want any function that's like not normal vector function, just encapsulate it. It's probably the easiest way to go. Then we have just curvature. Hey, polynomial, derivative, second derivative, magnitude, cross product, put them together, you got it good. Has this been explained well enough for you? I know I didn't do the cross product here, but I mean, come on, can you guys do cross product at this point?
Yeah.
Okay, then we're good.